When I agreed to give these 3 lectures and I decided I was going to focus on waste, yes, I knew it wasn't going to be a bundle of laughs, yes? It's not going to be a bundle of laughs. I have found giving these lectures quite arresting in kind of understanding what we have done to our planet in the last 70 years and 10. And in giving the lectures, I picked 3 different topics. Something new on the horizon, microplastics, where there's concern, but not a lot of hard data of risk and hazard. PFAS, forever chemicals, where there's good quantification, but still questions about how they impact on health. And I wanted to end it with something which has never actually gone away, where the quantification is excellent, where the health evidence is mature, where the toxicology is completely worked out, and where the overall investment is almost completely negligible. So I'm returning to lead, and for me, partly this is also a bit of a homage. My father was a plumber. His speciality was doing lead dressing on roofs. I grew up surrounded with lead workers all my life, yes? So, whatever your IQ deficit is from growing up in Sheffield, I think mine is multiplied by a factor of 10. So I'm going to go through this today, and really, lead is something which has been around since antiquity, yes? We have a long history of living with lead, and that belies the fact that it's not in our top 10 elements in our crust. I think the crustal contribution of lead is somewhere in the order of 0.0013%. It's actually a relatively minority element in the Earth's crust. It just happens to be present in a variety of ores. I've illustrated some of the mineral forms there, galena being the absolute key one, in a form which is actually relatively easy to smelt, easy to extract. And because it's often associated with silver, it was smelted relatively early for the extraction of precious metals. And the byproduct, lead, could then be utilized. And it could be utilized, the Egyptians, for cosmetics, but it could also be used for plates, items. And what I've got down here in this bottom corner is the oldest lead artifact. It was found in the Levant in Israel. It's 6,000 years old. It is a mysterious item, sometimes described as a wand. The important thing about it is that it actually contains lead. And isotopically, that lead comes from Turkey, where the first mines for lead actually were based. And there's evidence of lead mining in Turkey from 6,000 BC, predating the Bronze Age. So, this material has been with us for a very long time. It's been very useful, it's been used as a poison, it's been used as a cure. But we've also known that lead has harmful effects, and we've known it for a very long time. And I suppose the point at which lead really begins to take off is during the sort of Roman era, when the Romans begin to coin silver en masse to pay for their empire. And at that point, we begin to get lots of evidence of lead having detrimental effects on health. So here I have Dioscorides, who was a physician, a botanist, around the time of Nero. And he made the observation that lead makes the mind give way. There was already an appreciation that people who used lead cups, people who were imbibing wine that had been treated with sapper, which was an extract, a concentrated grape extract produced, distilled almost within sort of lead vessels, were behaving a bit strangely. In fact, there's even some argument that perhaps, some of the more colorful aspects of Roman history were influenced by lead toxicity, a bit of antisocial behavior, very poor conduct disorder, yes? A little bit of psychosis thrown into the mix. Julius Caesar's architect noted that he felt the water quality deteriorated in the aqueducts when they transferred lead-lined sort of ducts from earthenware. And sapa at the bottom, well, sapa is interesting, I suppose. It is this extract which was added to wine to make the wine more palatable. It was actually used all the way through into medieval times, where it was delivered as a sweetener, as lead acetate. And it was associated with saturine sort of conditions, with people displaying abnormal, strange behaviors. So saturine gout. So in antiquity, there's a realization that lead affects the brain. Already there's a realization. We have to go forward quite some time in history until we begin to see people turning a more sort of rational scientific eye on the issue. And I've picked Bernardo Ramazzini at this point because he really is the first person who began to explore the link between occupational exposures and some of the sort of cognitive and behavioral aspects of exposure to heavy metals. So he already noticed some of the tremors and behavioral problems occurring in individuals who were using mercury. But he also, in this treatise, observed similar sort of peripheral palsies occurring in potters who were using lead, copper, and mercury glazes on their pots. So, okay, we're in this period of time, we're beginning to see an occupational literature, an appreciation that people working with heavy metal ores and metal ores are beginning to manifest symptomatic responses. And this is just my opportunity to give a call out for all of the dead scientists, okay, who did a relatively good job at addressing questions. So, here we have Louis Troquel de Poncher, treatise published in 1836. Again, he begins to actually do larger studies, 1,200 cases of lead poisoning at his central hospital, beginning to look at the symptomatic responses of those individuals, beginning to understand that the symptoms were greatest in individuals who were exposed to lead fumes, as opposed to lead in other forms, lead via inhalation. So, we know lead's bad, okay? We know lead has adverse effects. This isn't news to anybody, and we're still in the 1800s, yes? I'm going to go forward a little bit because, and it will become apparent in due course. I think this is the first report that lead potentially has an impact on children's health. And it's a report published in Australia by an ophthalmologist looking at optical disturbances in children, which he begins, this is a sort of like an Australian BMJ article, he begins to speculate that this could be because they're exposed to water which has come from a lead-lined water tank. But then when he realizes that isn't at play, he begins to suspect lead in paint, yes? And it's actually a really lovely piece of occupational medicine in this paper, justifying his rationale, arguing that there is this exposure and people need to do it. And when the children were isolated from this source of sort of lead contamination, their symptoms sort of improved. But this was ridiculed at the time by the medical profession. So here we have the first evidence of lead having a pediatric impact on children developing in relation to leaded paint. Now, that's the first scientific sort of investigation of it. The next slide is a bit of a sort of, it's a bit of a vanity on my part because I found it and I had to put it up there because it shouldn't have been a surprise. This is an advert from 1897. The reason there's a bit of vanity here is it's from New Cross. I live in New Cross in London, so there you are. I thought that's entertaining. I found an advert about a business in my old area. And already in 1897, they're advertising the benefits of enamel lead-free paint because of the harmful effects they are conjecturing are caused by exposure to lead-based paints based on the occupational literature. They're making a jump of faith. Their product is lead-free. Already, this predates that paper in 1904. So, lead we have something to be concerned about. But when does it get hot? When do things begin to change? Now, I'm going to introduce you to one of the most, I think, interesting figures in 20th century history. This is Thomas Midgley. He has the distinction of being the man who invented tetramethyl lead and also, simultaneously, the man who created CFCs. When I was coming here on the tube, I was reading some more information about him, and I found some quotes, okay, and I scribbled them down in my book, because these quotes are just gold dust. And I hate doing this because, this is sort of, but these are quotes people have written about him, and they're absolutely spot on. So we've got J.R. McNeill wrote, "He's had more of an adverse impact on the atmosphere than any single organism in the Earth's history." Good start. Bill Bryson was a bit softer. He said that he had an uncanny instinct for the regrettable. Okay, that's quite good, isn't it? And then Fred Pierce wrote that he was a one-man environmental disaster. That's quite amusing. It's darker, to be frank, than many of us would think. And actually, within the darkness of reflecting on how we ended up pumping hundreds of thousands of tons of lead into our air, there are lessons to be learnt, I think, which resonate down the age in terms of the relationship between public health, the economy, and industry, and key players within it. So Thomas Midgley worked for General Motors. He was given the task of coming up with a product that would be an anti-knocking agent in gasoline engines. That was required. There was desire for it. Ethanol worked quite nicely, but it couldn't be patented. And so he developed tetraethyl lead as a patented form of anti-knocking agent, which could be monetarized. Then you could say, that would be fine. That would have been roughly 1923. 1924, there's a leak of tetramethyl fumes at the actual factory. About 5 people die, about 50 individuals suffer from lead fume intoxication, hallucinations, significant problems, all hushed up. Yes. Bizarrely, the man himself, in order to prove the safety of tetramethyl lead, inhaled it whilst washing his hands in it to prove that it was safe, and had to take 6 months off to recover, paid for by the company. So look, this is not ideal, yes? And we end up in a situation where we have tetramethyl lead being introduced as a fuel additive, first for the United States, and very rapidly the market grows, okay? So this is a mass release of lead into the environment, a compound known to be harmful and shown to be harmful occupationally by the people who are actually manufacturing it themselves. Then we find, I suppose, the next lesson, which is money speaks, but money is amplified when it meets the advertising industry. So the advertising industry now begin to really push this as a product. So we have the benefits, the automobile, the driver's benefit. Same thing also happened with lead-based paints. Lead-based paints were much better than the non-lead versions, and it was really strongly pushed. So the lead would still be used, so it could still be monetarized, so there would still be profit. All very well and good. This happens the whole time. Products are made, people turn them into profit, there are questions about their safety, fine. But this is a much more interesting story because of what happens next. And it allows me to introduce you to one of my scientific heroes and one of my sort of scientific villains, okay? And here they are. with the creator of methyl lead sandwiched in the middle. Here we have Claire Patterson, geochemist. On the other side, we have Robert Kehoe. He's physician, occupational toxicologist. They've become the chief sort of protagonists in the next period of understanding how we learn about the impact of tetramethyl lead. Now, Claire Patterson's a remarkable individual and probably would have been remarkable if he had never entered into the world of environmental toxicology. So this is a scientist who goes from the Manhattan Project and for his PhD and subsequent postdoctoral work ages the universe, just because that was the nature of that generation. By looking at isotopes of uranium to lead and different isotopes of lead in meteorites to arrive at an estimate of the age of the universe. Now, he's a wonderful analytical chemist, and one of the reasons he's my hero is he measures things. And we live in a society sometimes where people forget the importance of measuring things and measuring things well. Sometimes people think numbers just spontaneously arise out of some sort of science engine and they can use them. It was his regard for the numbers that uncovered the consequence of tetraethyl leads on the environment. And essentially, it can be summarized this. He couldn't measure what he wanted to measure, and he was about as good at doing it as you possibly could. Now, along the way, in order to try to get a measurement of lead isotopes, he developed the world's first clean room. So he was at Caltech, spent his entire career at Caltech. First clean room to try to get an environment where he could actually measure the lead within the meteorite without it being contaminated by all of the contaminating lead within the world we were living in. And he eventually did it. Eventually, in the clean room, with the mass spectrometer that he made himself, with the reagents that he synthesized himself, on the equipment that he manufactured himself, complete control of the entire process, he solved the conundrum. The universe is 4.55 billion years old. Went home, told his mother. She was probably unimpressed, yes? Okay. But he couldn't get over the lead issue. Why was it so difficult to do? Why was there so much lead in the environment? And he raised issues about that. He raised issues of there's too much lead, and everybody said there's just a normal amount of lead. And so he went on to do some remarkable studies. And herein is a bit of a debate. He wasn't taken seriously. And he wasn't taken seriously because he was a geochemist. And he was drifting into a world of medicine. And the medics and the toxicologists and the health professional, I'm one of them, weren't keen on this person coming and telling them how to do things. But he began to do studies, and some of the studies are really seminal. He looked at lead levels in the ocean. And he discovered that if you went from the top waters of the ocean to the deep waters in the ocean, there was a 20-fold gradient in that column of lead concentrations. And because of the way in which water circulates in the deep ocean, that kind of inferred that the lead, which was accumulating in the upper levels of the ocean, represented lead which had represented the last 100 years, suggesting there had been an enrichment of lead. He then went on and did ice core studies. He did Greenland, he did Antarctica, looked at the lead accumulation in the ice cores, got very much the same sort of information. An increase of lead in those samples during the Industrial Revolution, and then suddenly supercharging around the time that tetramethyl lead comes into production. So, he said a number of really salient things. Said, okay, there is lots of lead around, but it's a new normal. It's not normal, yes? Normal was 100 years ago. The levels now are artificially inflated. That is an incredibly important observation. He talked about the fact that tetraethyl lead was probably the culprit, but he also mentioned other pieces of the jigsaw as well, and he suggested we should do something about that. And of course, all of those things are technically the death nail to a successful industry making tetrol ethyl lead. So they have their defender. And their defender is Robert Keyhoe, who was a toxicologist preaching the mantra that this is completely normal, these levels are completely normal. And he actually introduced in a whole series of hearings something which is known as the Robert Keyhoe paradigm. And it's an interesting paradigm because it dominated the way in which this field developed for quite some time. He argued that if you wanted to criticize or say something about tetraethyl lead, you had to be able to produce evidence which was absolutely crystal clear, no uncertainty, before the company had to do anything in order to potentially mitigate against a risk. So essentially, he set up a paradigm which was argued, and it was adopted by the government, that allowed the industry itself to police itself, to design its own studies, and is almost the reverse of the precautionary principle. You know, the precautionary principle says, don't put something out into the environment unless you know it's safe. His argument was, if it's in the environment, prove to me it's doing harm. And that's actually quite a difficult thing to do, to a level of certainty that's going to result in people taking action. So these battles went on for a very, very, very long time, until eventually it was accepted that this tetraethyl lead build-up within the environment had occurred, and after it occurred, preliminary evidence began to occur showing relationships between blood lead levels in children and impacts on cognitive function, and perhaps the thing which really changed the debate, impacts on intelligence quotient in those children as well. Now, none of this should have been a tremendous surprise. This is a graph of global production of lead from prehistory to the development of smelting technologies to the classical era to the period of expansion of the Roman Empire and silver coining. You can see it going up, then it falls down again during the sort of medieval period. We hit the medieval, the Industrial Revolution, it kicks up again, and that kick up also occurs because new lead mines are opened in South America and in Australia, and so lead suddenly becomes cheap, and that pushes lead production as well. So we have this increased lead production. We know it's going to go somewhere. We're manufacturing it, it's being used. And actually, the ice core data is just exquisite in terms of anticipating how this affected the global environment. So I've pulled some data from Joseph McConnell, 2 papers published in the Proceedings of the National Academy of the sort of USA. And these are fantastic. So this is looking at lead in ice cores taken from the Greenland ice sheet. And it represents sort of like the production of lead during the period of time. And here, you can begin to unpick how that production of lead correlates to the fallout of atmospheric lead onto the ice sheets, which then gets incorporated into ice sort of cores. We can see the Iron Age, not much going on, quite quiet. Classical antiquity, okay, we have the Roman Empire, we have the crisis of the Republic. There's some interesting stuff here, okay, when there are political sort of upheavals and economic downturns, actually pollution seems to improve. Then we have Pax Romana, and we can see it goes up again, and those little dots relate to the coinage density at that period of time, and then the Roman Empire collapses, lots of plagues occur into late antiquity, and it's really not until the early medieval period that lead begins to appear in our atmosphere. So we've got a fingerprint. We can see human activity in terms of lead production, and then we can actually begin to cascade that forward in time. So again, here we have 3 ice cores from Russian Arctic, North and South Greenland, picking this up from about sort of like the point we were at before. So here we are in the sort of like, so let's go Republic, Pax Romana, in the Middle Ages, now into the Carthaginians, the Great Famines, bang, Industrial Revolution. We can see this increase. And just bear in mind, this is a log scale, okay, in terms of the concentrations of lead falling out of the atmosphere in prehistory to the modern day, illustrating that this is a real sort of issue. So, lead is bad. We know that. We know it has neurological complications. We know that it has them in adults and it has them in children. We know that there's lots of lead which has entered the environment. And whilst it's locked up in rocks, it's pretty safe, yes? Once it's mobilized and worked, then we've got a bit more of an issue. And I suppose one of the reasons I focused on lead, of course, is that once you've mobilized it, it doesn't go away, yes? What has been released is there forever, yes? It is the legacy that all subsequent generations will have to live with. But why should we be concerned, and where are we now in terms of thinking about this? Where are our lead exposures coming from today? And I suppose that's when it begins to get interesting, and in terms of thinking about whether lead is still an issue today. I think many people don't think it is, and if you're one of them, be prepared to be quite surprised just by the numbers I'm going to give you. Lead pipes, clearly. That's a straight thing. Lots of sort of containers, plastics. I mean, plastics, actually, many old plastics had lead incorporated into them, PVC particularly, to make them more pliable. We have paints. Lead paints are still available. I was quite surprised to find out that there are still about 48% of countries haven't banned lead paint. I thought that was a global ban, but that hasn't happened yet. We have occupational uses. We have traditional medicines and spices, which I'm going to talk about a bit later on as well, as a potential source of lead contamination, which people just don't think about. And all of these things we are exposed to either through ingestion or inhalation or through contact, all of which can be taken into the body. And then we have a range of health effects. And I suppose if there's a take-home message I'm going to try to force out of this talk about lead is that there's this idea that it's neurological. Yes, it has neurological effects, and you know that. It has significant cardiovascular effects as well. In terms of absolute quantification, probably the burden of disease through cardiovascular causes is greater than that attributed to the impact on the brain. And I don't think that's appreciated, and it's only when you appreciate that some of these numbers downstream begin to make sense. There are reproductive issues. There are links to chronic kidney disease. There are increasing pieces of evidence linking accumulation of lead in bone to osteoporosis. The sort of lead begins to replace calcium, and as it begins to reduce calcium, it induces weakness within the bone. And that, in part, relates to the way in which our body stores lead, which sounds kind of crazy. So a lot of the lead we inhale or we eat in our diet, we just excrete, or it passes out in our feces, yes? We have some which will enter the blood, and then it will partition throughout the body into either soft tissues or into hard tissues. 96% of your lead, which you've accumulated over your lifetime, will be accumulated in your skeleton, okay? Or your teeth, in hard tissues. A relatively small percentage is in the blood. Most of that small percentage in the blood is actually retained within your red blood cells, about 99% of it. And those ratios change a little bit depending on whether you're an adult or a child. The consequences on the brain, if we just focus on these to begin with, and I think they're interested, are in early life, I've got sleep disturbance, behavioral disturbance, anxiety, cognitive development issues, a whole host of verbal challenges, all of which have been proven and related to lead exposures in the blood of between 0.1 to 30 micrograms per microliter. Now, there's a story here which is going to come out because we're going to talk about the way in which lead in blood and lead in tissues has decreased. But right from the bang, let me point out, it's now accepted there is no safe level. yes? There does not seem to be a safe level for lead at all. In adults, again, we see cognitive impairments, and those cognitive impairments, which are kind of done by association, blood lead levels in association to these effects, are actually supported by clinical outcomes, low birth weight in children, but also mechanistic data in terms of metabolic changes within tissue. So there's actually some real science. This is one of those areas where it's not just epidemiology showing an association. We actually have really good data on how lead causes the toxicology and the damage which brings about these impacts. Now, one of the other things which I think is important about lead and the brain is that normally the brain is a pretty protected environment. Now, the next graph is ridiculously complicated. It's the best one I could find. Simple stuff, yes? The brain is normally protected from the outside world by the blood-brain barrier. Really tight junctions, yes, to restrict the passage of exogenous materials from the blood, toxins, infectious agents, into the brain, because the brain is a protected environment. But lead doesn't have a problem, because lead has transporters which are just there to help it move across that blood-brain barrier. One of them is known as the divalent metal transporter 1. It can just go straight through that. It can also go through calcium channels. So the blood-brain barrier is not a barrier to lead. So it has access, once it's in the circulation, to get to the brain. Once it's in the brain, it has a plethora of cells it can interact with. So we have some neurons there, a neuronal junction, and then we have these two cells here which look a bit like amoeba. At the top, that's a glial cell. That's kind of like the immune cell in the brain. Down here, we have an astrocyte, which kind of plays a sort of maintenance role within the actual brain structure. And you can look across here, but essentially what happens is the lead has the potential to basically disturb calcium metabolism in all of these cell types and to cause oxidative stress, i.e. it will end up causing free radical production, which affects neurotransmission and actually can result in neuronal cell death because it triggers inflammation within the brain. So we have a toxin, I should say a toxicant. I should always say this to my students. Toxins are biological, yes? Toxicants are inorganic, so lead is a toxicant. We have a toxicant which can be taken into the body through the gut, through the airway, move and partition through the blood to soft and hard tissues, and has access to the brain. So this is actually, it's ticking a lot of the boxes for something you don't really want to release into the environment. And this is just to make that point about the way in which it partitions from food, air, contact into the various tissues. Because I think you've got to bear in mind that in the blood pool, lead has a half-life of around 28 to about 36 days. In the bone, for years, yes? It can be mobilized from the bone under certain conditions. The bone actually acts as a sort of storage organ for the heavy metal, yes. It should be doing it for calcium, but it's been replaced by lead in this circumstance. Which means that when you take a blood sample from someone to measure lead, what you're actually measuring is recent lead and old lead in a dynamic exchange between the body stores, yes, the soft tissues, the hard tissues. So it's a much more complicated sort of relationship than people generally think. But that's important. And the thing about bone, and I find this fascinating, is that there are moments in which bone will let go of the heavy metals, including lead, that it has accumulated. And one of them is pregnancy. So during pregnancy, lead will be mobilized, and it will be mobilized to the developing fetus. Yes? First child is going to get that hit. Yes? The other time it's going to get mobilized, there are other examples, is during menopause, when the lead is going to begin to become more mobilized into the tissue. I was looking for some nice pictures of bone because we do have some studies going on in my department at the moment looking at lead accumulation in bone because we're interested in osteoporosis and how that might work. But what I found instead were teeth studies. And again, this is quite nice. So this is a study of human teeth. And this is from Malaysia, so it's looking at the ethnic groups within Malaysia. So we have Malay, Chinese, and India within Malay. And they're looking at the dentine in the teeth as an accumulated tissue for heavy metals. And if we just focus on just lead here, we can see essentially that ethnicity doesn't make a huge difference. And that's there really as a proxy for dietary differences between different ethnic groups. This is the more interesting one, because what you have is 15 to 30, 31 to 50, 50 over, and you can see as you age, you begin to just increase the actual long-term concentrations, the accumulation of heavy metals within the body. So we are accumulating this stuff. We become biological accumulators of a toxicant, which we know has adverse effects on health. I said we knew a lot about its toxicology, and we do, and I could bore you all to death endlessly about this because this is my world, but here are some simple things that it does which cause problems in the human body. Lead will bind to little groups known as phial groups, which are often on proteins. When it binds to them, it can inactivate enzymes. And many of those enzymes are involved in the generation of heme in red blood cells. So lead, by binding to the enzymes which are involved in heme production, can result in anemia. Good, so you have an anemia signature. The body is full of lots of molecules which have these phial groups because they're really good sponges for free radicals, yes? In fact, there's a small molecular weight sponge called glutathione, which is throughout all the tissues in the body. But if it's bound to lead, it doesn't function in that way, which means you've reduced spontaneously that barrier. And in addition, some of the enzymes in the body, I've got two here. SOD stands for superoxide dismutase. GPX is a glutathione peroxidase. These are enzymes which also function to mop up dangerous free radicals. They're inactivated by lead. So if you knock out the low molecular weight sponge and the enzymes, go figure, the number of free radicals in your system goes up. You get a condition known as oxidative stress, and as the oxidative stress goes up, you move towards cell death, yes? So it can actually have generic effects in that way. And as I mentioned before, it really messes up calcium handling in cells, and calcium is absolutely fundamental to cell signaling and cell maintenance and metabolism. So just the lead in the system itself can dysregulate the whole system. Now, all of this is really bad, but I'm now going to give you some good news, okay? I know, it's not like me. I'm probably going to break after I've done this, okay? Although it says at the top, it's catastrophic, well, clearly methyl lead was catastrophic. But because of the science by Peterson and by the health professionals, it was realized that it was bad for human health, and it was banned. More accurately, phased out in a staged and graded fashion, as these things often are. But for me, here's another message, because what this tells you is regulation works. So here we have the percentage of children who have a blood lead level greater than 10 micrograms per deciliter. So that's the sort of threshold level at the time they did this. And here we have a timeline from 1971 through to 2008. And the red line is looking at that percentage of children with high blood levels relative to the lead-based Paint Poisoning Act in the United States, the phase-out of gasoline beginning in 1973, bans on residential painting in the States in 78, ban on lead plumbing. And you can begin to see, as all these regulations come in, the proportion of children with high lead levels falls. That, I think, is a biomarker of success and tremendous public health success. And the blue line over here just relates to the actual pure measurements of the actual lead. Now, just bear in mind, we're still above 10, sort of 2 to 10, in terms of the proportions. Now, that's great, that's the United States. Just for the sake of argument, that's when the United Kingdom banned leaded gasoline. That was at the beginning of 2000, January 2000. And that's when we banned leaded paint. So that puts us onto that spectrum. But the world did not become lead-free or tetraethyl lead-free until August 2021. Again, not appreciated when Algeria was the final country to ban the sale of leaded petrol. With one caveat, and it's a caveat that I only found out about this week. It's one of those habits of when you produce these lectures, you read around, that I've just discovered that if you have a piston-operated light aircraft, they still use tetrol-ethyl lead in their engines. And I had no idea that was still the case. There seems to be a bit of a loophole. So that's an interesting one. Now, this has been tremendously successful. How successful? Look, here we have blood lead concentrations across Europe from the mid-70s through to the present day, and you can see how concentrations have fallen in children's blood. Tremendously successful. And we can go on, we can also look at that in terms of the concentrations in North America. Success. So why should we be concerned? The science has evolved. And what the science has now told us is that lead at much lower levels than we previously thought has impacts, particularly on cardiovascular health. And I've stolen this. This is a dashboard. This is great fun. If you follow this little thing, it will take you to the dashboard for the global burden of disease. And you can pick your disease, and you can pick your environmental stressor, and it will tell you how your stressor contributes towards the global burden of disease. And this is the global burden of disease, total mortality related to lead. And you can see here we have IHD, that's ischemic heart disease, stroke, hypertensive-related heart disease, and down here we have chronic kidney disease. So you can begin to work out what the global burden of disease is because of lead. And then we can put some numbers on it. And we can see that although the concentrations have gone down, actually the science is suggesting the risk has gone up. So in 1990, if you do this exercise, you get around 500,000 excess deaths because of lead globally. In 2019, which is the last time this exercise was done, we are up to 900,000 premature deaths. If we don't get completely obsessed with death, and then we also begin to consider what the impact is on your day-to-day living, your morbidity, yes, and we can actually then begin to deal with things like developmental disorders and how that begins to impact on your life, well, then we can put some DALYs, disability-adjusted life year estimates on this, and we can see that, okay, let's just look at the headline figure for sort of now, and we can see we're looking at around 21.7 million disability-adjusted life years in the global population. These figures are chunky. There is no other chemical entity which gives a number of this magnitude, yes? Hardly any investment. Now, most of this burden is in low and middle income countries. The terminology here is a little bit thing, but you can certainly see Pakistan, Bangladesh, India lighting up dramatically here in terms of areas where there's significant high levels of blood sort of concentrations in children. And if you want to put that into sort of quantification, India, China, Nigeria, Pakistan, Indonesia, these are millions of children with unhealthy levels of blood lead. Okay? This is chunky, massive. In fact, if you estimate it, you have about 800 million children and young individuals under the age of 19 who have blood levels at concentrations known to be harmful under current research, and very little investment in research into this particular area, compared with microplastics or compared with PFAS. Hence the reason I picked this one as my last example. And the science is great, and the science is really good. I'm going to just fly through some science here. Look, this is a study. It's based on a sort of survey, a longitudinal survey of health in the United States, the National Health and Nutrition Examination Service. Here we have adjusted blood levels, and here we have if you have sort of like diastolic and systolic blood pressure. And actually, it doesn't look as though there are many dots, but those are average dots. There are about 500 pieces of data on this. And you can see there's a relationship between blood levels, lead levels, and blood pressure. And if you take that data and then you convert that to risk, you can begin to see how mean blood levels correspond to predicted deaths from myocardial infarction or from strokes. And you can see it's a curve which goes all the way down to very, very low concentrations indeed. And the data gets better. That's quite odd. I picked it up there because it's from 1985. It was one of the first studies which looked at this cardiovascular risk effect. Here's something a little bit more recent. This is from Lancet Public Health 2018, and it's again looking at that survey in about 14,000 individuals, and just look at the cause. All-cause mortality, cardiovascular mortality, ischemic heart disease, concentrations of blood lead, that's 10, 7.55, 2.5. Look at that black line, that's the effect, and you can see that it's going down towards zero, down to incredibly low levels of blood lead concentrations. And over here, this is really nice because they've put lots of things which are associated with increased cardiovascular risk. Cigarette smoking, lack of activity, high cholesterol, glycated hemoglobin, and over here we have the effect estimates. At the very top, you have lead. And you'll see that lead is one of the strongest predictors of all of these indicators, not appreciated by the general public. If it was, I think there'd be much, much more focus. Now, once you've got those relationships, you can begin to do proper evaluations globally, look at the risk, and try to quantify it. And again, something which is very new. So this is from October this year. This is looking at IQ loss across the global population. So this is cumulative IQ loss across blood level concentrations. And again, we can see the line goes down, and clearly we're still seeing IQ losses beneath 10, 5, and 3.5, which is what the CDC recently said we should be concerned about. Okay, that's quite a lot of IQ loss. In fact, I think it's about, I wrote it down because I myself couldn't quite wrap my head around the magnitude of the loss of IQ points, but it's pretty hefty. This is the cardiovascular risk. Again, parts down. Now, the reason I've done this is they use this to do an economic evaluation. Economic evaluations really matter, yes? Because that's how people think about these things. The costing of lead, based on these IQ effects on children up to the age of 5, and cardiovascular deaths, came in, and literally I fell off my stool when I read it, at $6 trillion US dollars per year, or 6.9% of global GDP. Now, you can argue about the figures, yes? They can go up, they can go down. However that number goes, it's hefty, yes? And certainly worth people's attention. Now, it's difficult when you do those calculations to deal with the impacts on the brain in children. And I just wanted to say this, and the reason is, when you start looking at childhood disabilities related to poor cognitive development, that goes all the way through to crime, antisocial behavior, lifestyle impacts, all the way through. And those aspects have not been fully quantified to the present moment in time. So, okay, big effects. Now, I'm going to rattle through some things to keep you nervous. The lead never went away. This is a study my colleague, Dave Green, and colleagues, Roy Harrison at the University of Birmingham did, measuring lead and lead isotopes. Busy road in central London, Marylebone Road, there's an air quality monitoring station. If you look at the isotopes, what you work out is about 40% of the lead you measure in the air comes from tetraethyl lead. It never went away. It just got retained into the soil, into the roads, so it could be kicked back up into the air in the passage of waking vehicles. Important message. What we put out into our environment stays there. Lead is a classic example of this. And we have a few things that I think we need to be concerned with. Batteries. We're obsessed with batteries. And we're very good in the West at making our problems disappear by shifting them to the developing world to get them to deal with it. This is India. This is somebody recycling by hand lead batteries and actually smelting the lead out of them in an open pit. Yeah, this is quite common. It's estimated that 90% of lead batteries in India end up being recycled under these unregulated things. And here's an interesting one. This is the concentration of lead in controls and people who are doing this work. And you can see this huge additional lead concentration through this unregulated work. And associated with that, the people who are working in these fields have a significant increase in blood pressure. They also have decreased lung function. Clearly, this is not an ideal working environment. So, batteries. Some people argue that the fact that lead is still high is because of this battery recycling issue, and it's something we have to address. Here's something else we have to be concerned with. I used this slide before when I talked about microplastic, but tires use lead in the vulcanization process in their manufacture. And this is data from some colleagues at the MRC toxicology unit. All they did was grind up lots of different tires from cars and lorries and measured the actual metals associated with them. And right at the end, cars and HGVs, a source of lead. So as you drive around and your tires are ground into the road, we have a new source of lead entering our environment. Plastics. I mentioned plastics before because lead had historically been used in toys and plastic manufacturing. It's been phased out here to a certain extent, but not everywhere. And we still import a lot of very cheap goods from other countries which don't have such high regulation. And here's the other thing. We want to recycle that. And so all of the old plastic we are recycling, potentially we are recycling the lead and all the contaminants which is in that plastic when it was originally manufactured. So lead is still an issue when we start thinking about plastics and microplastics. And then food. This is something which took me by surprise. This is turmeric, yes? Apparently, if you want people to buy your turmeric, it's really good if it's bright yellow, orange, yes? And the best way of doing that is to add lead chromate to it. And so, in other countries, this is in Bangladesh, they add it and then they export it. And so actually there's quite a high level of lead within imported spices coming into the United Kingdom and Europe in general. And you can actually begin to quantify the concentrations of how that lead builds up in the soil outside these facilities, in the dust, in the mineral dust, in the pigments which they're putting. So you can actually see how the lead is accumulating in the industrial process. So lead is not gone away. Yes, the lead we put into the environment is still there and recycling, and we are still, as a society, making things and introducing lead into our environment. So, I thought I would therefore end with this. I wanted to talk about waste, and I've been unreservedly negative and depressing about it, which is to break the fundamental paradigm of giving a talk, which is you're meant to leave the room feeling happy and as though the world is a better place. I think it's time we all woke up and stopped entertaining ourselves and distracting ourselves, because we're in a perilous situation. In fact, looking at the great challenge of our age. These are the planetary boundaries defined at various points, and this graph illustrates how far we are exceeding our planetary boundaries. So this is 2023. We have, we haven't quite got to stratospheric ozone apocalypse. Atmospheric loading, not too bad. Ocean acidification, we haven't killed everything quite yet. Biogeochemical flows, we've messed that up. Fresh water, we've messed that up. Land system change, that's messed up. Biosphere integrity is in shocking state. Climate change, we know the direction that's going at. And novel chemical entities in our environment is off the scale. This is not a time for being unrelentingly cheerful unless you're doing something about those issues. And so here are some lessons. Lead, ... insert whatever comes next, because it's coming. Somebody is about to monitorize a new chemical and release it into the environment without safety testing and without any regulation. We know it's going to happen, yes? It is a continuing issue. The anthropogenic material we put out there stays there. We have to live with the consequence. One of the reasons the public, I think, struggle to wrap their head around these issues is that we think about poisoning, we think about occupational exposures, high exposures. We don't think about the consequences of low-level exposures over decades on health and how that causes chronic disease. And if we don't understand that, we don't embrace it, then it's a very difficult narrative. The story of lead tells us something very important. If you want to change things, you regulate. Yeah? Education is great. I don't think, and I'm an educationist, I think education is good, but education on its own doesn't change anything. There's lots of ways you can avoid change. We need to think about the whole planet. I know that sounds a bit green and sort of a bit tree-huggery, but it's actually to do with actual sustainability of the planet we live on. And another thing, we need to stop exporting our problems elsewhere and claiming that we've solved them, because we do that a tremendous amount, and it really is completely a dereliction of the duty of an advanced society. Now, I'm leaving you on a positive thought, therefore. Please feel free to insert your inspirational quote. My inspirational quote is this: it's time to do something, yes? It's time to accept the magnitude of what we have done and to make a positive decision to change the status quo. The status quo doesn't guarantee us, I think, a very happy next 100 years. Thank you.
God, you're depressing. It was absolutely wonderful talk and really, really scary, as you might expect. I'm not sure if I missed it in the middle of all that lot, but imagine a child living on the edge of Marylebone Road or South Circular. What do we know about their individual blood lead levels being associated with being next to a road, for example, like that?
At the present moment in time, at these levels, probably not enough. There's a study going on at the present moment in time, probably for the first time in a couple of decades at Queen Mary's University, where they are actually going in and looking at blood levels in children to create that data set. We've been very neglectful, yes. I think there's been an assumption that the problem was solved, yes, because of the regulation, the concentrations falling. But now we know that there are health effects at these lower levels. I think it's important. And to pick up on your point, we have a tremendously inspired way of doing things in planning in the United Kingdom, especially in our cities, in that we do like building high-density housing developments next to the busiest roads, yes? Now, you might argue we don't have lead in petrol anymore, but it now turns out we are still resuspending the historic lead and we're introducing new lead from tyre wear. So yes, I think we do need to work out what's going on.
And there's a sort of funding research question which interests me about a lot of this. So I used to do medical research as well, but you very often find your funding cycle is 3 or 5 years. And what you're looking here is lifelong change in these people. So collecting real-world data over long periods of time surely remains a funding challenge for people like you.
So, I'm always going to say that what we need are longitudinal cohorts, large populations who we follow routinely across time, yes? I'm involved in a number of them. They are very draining, very hard on the people working on them, because it's not a quick win, yes? You are investing in something for 5, 10 years before you get a positive paper out of the whole process. But they are the only way forward, especially if you're trying to look at the way in which a chemical in an environment contributes to disease causation. Once you have a disease and you're just asking, does it exacerbate a symptom or some sort of diagnostic criteria, well, then that's easier, yes? But this is about disease development. This is about the causing of non-communicable disease. Therefore, you need to start in childhood and you need to follow populations through. Funding will always be a battle because that's very expensive.
Thank you very much. That was really an interesting discussion. In the 1990s, I did a comparative study of policies to deal with lead pollution, comparing the USA with the UK. And the impression I had then was that the USA, in the ways you indicated initially, were trying to do something about it. And my summary of the position in the UK was that the UK government had never set a lead reduction target until after it had already been met. Do you think that remains the case?
Ooh. Almost certainly. Well, there's only one caveat to what you've said, which I agree with, yes. Which now the tendency is to set a target so far in the future that you will not be responsible for the delivery of it, yes? So this is how it has changed. They have evolved, yes? Now you promise the change in 20 years' time under some other political climate, yes? So the words are fine, but the delivery isn't great in the short term.
I wondered, I listened to your PFAS one as well, and that had a pretty similar conclusion. Is there any hope for remediation for lead particularly, but really any of these big issues?
Yeah, I think there genuinely is. If you're willing to invest in the solutions, I think there are solutions to many of these issues for remediation already, yes. The issue is that they're very expensive, and the remediation won't happen unless it's economically favourable for it to happen, yes? And at the moment, it's just a cost, yes? It's a cost which people don't want to meet. So you have to regulate, yes? If you regulate and say you have to do this is the remediation, then suddenly everything changes, yes? Money becomes available, innovation happens. So I know, perhaps you could imagine that I'm very pro-regulation and very anti-business. I see regulation as being the engine to create new business opportunities, yes? New innovations, new solutions, but actually focusing on solutions and sustainability for economic growth as opposed to just throwing chemicals into our environment.
I mean, it's a very optimistic
No, I'm
summary.
going to sit down in a second.
Yeah. When there's so much emphasis on growth and emphasis on rapid growth of companies to achieve that growth, people take shortcuts. And as you rightly point out, people are generating new stuff all the time. And we have, I can quote, the bonfire of the regulations as policy decisions. You're in a minority, I suspect.
Oh, I usually am.
I know that.
But I would look at it this way. Somebody's going to pick up that cost. Yes? That cost is coming. It's not going to happen. Those health costs, those economic costs will be delivered to our children and our grandchildren in a degraded environment which they didn't deserve. Yes? So at the present moment in time, I don't think that's adequately costed into long-term projections. When you focus on growth, I think there should be a denominator about how much that growth is going to cost in terms of environmental degradation and in health costs. And until that's done carefully, you won't know if your growth is actually an illusion. Yes, and actually you're growing in the short term, but losing mass GDP in the long term.
Thank you. Given what you've said, would you say that schools and indeed blocks of flats should never be situated right near really busy roads, A roads, or extremely busy roads?
I've been saying that since the year dot.
Yeah, how does one
So
object to it in planning applications? That's the point.
I have some sympathy for certain environments in London because they're historically there, yes. I have no sympathy with new developments which are ignoring known and present environmental risks and usually coming up with very, very nebulous justifications for why they don't apply to them.
Are there any examples of countries that maybe aren't addressing things perfectly, but are nonetheless making a better fist of things than perhaps the UK is?
So, what's the correct word to say there? I believe if I was a politician, I'd say it's unhelpful to compare other countries' performance because of the, clearly there are countries which do a better job of balancing economic growth against social justice, dare I say that, and environmental sustainability. Many of them are in the north of Europe. The irony is, of course, the countries which do the best job probably have the lowest risks. And the places which we need regulation where most of the people live and most of the people at disadvantage are very deregulated areas. But you can't tell those countries how to govern themselves. All you can do is deliver data and hope at some point the data wins. That's the curse of the scientist is we don't change things, we present data and hope, with fingers crossed that things will happen.
Well, 2024 is the year of elections. You have your chance to influence people and ask for more data. Ian Mudway, thank you very, very much for another wonderful lecture. We're really, really sorry to see you go. It's been great working with you. Thank you very much.